Hello, I am Ryan from Venus International Snayan, and this is our paper with Hanif, which is my teammate. So, our paper is about predicting tsunami risks from earthquakes in Indonesia using machine learning. So, this is our table of contents, so we know what I'm gonna talk about. So, the introduction is straightforward. We're just gonna do the introduction of our topic. Related works, I'll talk about it a little bit, not too much, just so everyone can get an idea. And methodology, so this is more in depth. Results is our results, and visualization is we'll be talking about the visualization of our outcomes and the conclusion. So for the introduction, so as most of us know, but for those who don't, Indonesia is a country consisting of thousands of islands situated in the wide ocean, lying along the Pacific Ring of Fire. So we are, right now, Indonesia, we are around a ring of fire. Due to that, we have Indonesia has high risks of geological hazards like earthquakes and tsunamis. And in recent developments, Indonesia showed promise with the Sitorus demonstrating successful pilot earthquake early warning systems in West Java using the BMKG network data. So I'm just gonna glance over this slowly. So I took this from our research paper so this is how it goes. So for related work, there is Mulia. He used machine learning algorithm for a real-time tsunami induction prediction. They utilized offshore stations as well as offshore observations along the southern Sanriku coast of Japan. Meanwhile, my team, we are focusing on the local systemic data, so Indonesia. Compared to them, they focus on real-time tsunami inductions. Same with here. Our study for Mulia, so our study focuses on assemble and traditional machine learning models. So this is our methodology. So this is data set overview and the descriptions. So in table I, which is table 1, so it shows the main attributes of our earthquake data sets. So the event ID and date time fields help track the individual earthquakes, while the latitude and longitude mark where they occurred. So overall, this is like our data set overview. So this is what we use, as you can see. This is more in depth also. So this is our workflow. This is our workflow. So from Kegel Earthquakes in Indonesia dataset, we will bring it to catalog. Then we'll convert it into CSV, then data cleaning, merging the data. And from the repository to EQ repository and then data cleaning. So these, the top and the bottom, are all going to merging the data, as it says, merging. And table 2, this is a summary of our key findings, like the features, so like depth, azimuth gap, phase count, latitude and longitude. So this is just explaining what it means. Like this is coordinates of the earthquake epicenter, phase count is count of systemic wave phases, and so on. And table 3 is visualization of prediction trends. So these are visualizations like trend lines, cumulative analysis, and ROC curve. And this is the description. So now we will go over the results. So model comparison. So first we compared 4 different models: logistic regression, decision tree, random forest, and gradient boosting. So the best model so far is gradient boosting because it balances precision and recall, and it's the most reliable. While the other models like logistic regression, it has a low precision of 0.5 and many false alarms, while the decision tree has okay performance but is very easily overfit, so it's like less reliable. While random forest has a strong performance but has lower precision versus the gradient boosting. So overall, gradient boosting is just the most balanced of them all, as you can see from this table. So this is our visualization. So these are just talking about it. So red dots around these maps are high tsunami probability. Blue is low probability, as you can see. So this shows the predictions at earthquake's epicenter. So like I said, gradient boosting, as we said, is the best. Highest accuracy, effective use of features like phase, count, depth. High confidence in tsunami prone areas. As you can see here, the bottom right is the gradient boosting. It has high confidence in tsunami prone areas, like I said, Sulawesi, Maluku, and lower confidence in safer areas like Java and Kalimantan. So for our conclusion, so this study helps enhance the tsunami risks predictions in Indonesia through the use of machine learning, with like gradient boosting emerging as the most reliable due to its high ROC AUC score and of course balanced performance. So by removing the magnitude as a predictor, the model achieved greater robustness and reduced overfitting. And this shows us that it's very valuable for overall strengthening the early warning system to prevent disasters from happening, so people will be safe. So looking forward in the future, we can improve the system by integrating real-time seismic data, offshore gauges, and satellite imagery to broaden prediction capabilities. So applying this learning methods such as RNNs and transformers may further capture complex seismic patterns. So in the end, we would like to, in the future, evolve our project with the things I talked about, and overall also this study will hopefully help Indonesia with the early warning system and disaster to help everyone. Thank you very much for listening and watching our presentation. And my name is Ryan, like I said. And if anyone has questions, feel free to ask. We will answer them the most we can. Thank you very much.